Question 15 of SMOPS 2016. So this is a very common type of question in Maths Olympiad questions, and I hope this video really clears it out once and for all, right? Really try to pay attention to this video, right? Get this one question down and you'll be able to solve a lot of questions in the future. So the leading question I have for you is whether counting zeros is essentially the same problem as counting the powers of 10. Right, what do I mean? Let me give you an easy example. How many zeros are there at the end of 10 times 10 times 10? Right? Some of you may do this very, very quickly. They can tell me, it's 3. But if I change it up a little bit, 20 times 10 times 10 times 10 times 10, some of you are, again, very fast. You can tell me that's 4. Right? But I really want to prompt you guys, how did you get these numbers 3 and 4? Right? One way you can do it is just really calculate it off, right? At the rate numbers here, 1,000 and 20,000. Then you just count, right? But some of you are very fast, you just notice that, hey, I can just ignore the digits at the front. The 20 doesn't matter, the 2 doesn't matter, right? Just ignore that one and count the number of tens, right? So the power of 10 for the first one was 3, 10 to the power of 3, so there are 3 zeros. The power of 10 and below, right, I can pull out 4, so I have 4 zeros. Let's try something more complicated, 12 times 10 times 10 times 10. And this is where some students may falter and say, there are 4 zeros. Because 12 is bigger than 10, right? So 12 times 10 times 10 times 10 should be 4. But that's really not the answer. Let's double check. We actually see that when we just calculate it, it's 12,000, right? And we look at it, we just count with our fingers, 1, 2, 3. There are 3 zeros at the end. The reason why it's very simple, we ignore the digits at the front. The 12 really doesn't matter. The whole 12, just throw it away. We don't care about it. We cover the 12. We count the digits at the back. We count the number of 10s. That's good enough. So for the first question, there are 10s, right? There are 3 10s, so we're able to solve it. But the second question is now tricky, right? Notice there's no 10, right? 1 times 2 times 3 times 4 times 5. They are all smaller than 10. How come you have 120? How come there's a 0 at the end? Notice! Right? 2 times 5 is still 10, right? So the whole expression is actually the same as 1 times 3 times 4 times 10. There's still a 10, right? It's just hidden. And this 10 has been broken up into 2 times 5. Can you break it up even further? No, you can't, right? It's just 2 times 5. No other numbers can multiply and get you 10. So that's the trick, right? As long as you notice this, you really can solve a lot more questions, right? I'm going to change this up, right? The goal is to really just ignore the digits at the front. Just count the number of 10s. That's really good enough. So let's break that down into steps, right? Step 1 is ignore the digits at the front. Step 2, count the number of 10s. How do we count the number of 10s, right? We roll backwards. We just count the power of 10, right? 10 to the power of 2 has 2 zeros, right? That's 100. 100, we count it using our finger, that's 2. 10 to the power of 2021 has 2021 zeros. It really doesn't matter. We count the power of 10. But we also have to ignore the digits at the front, right? How do we do that? We factorize the powers of 10. So if it's something like this, the question hasn't changed, right? I just want to add in all these numbers. It hasn't changed. I don't care. 12 can be bigger than 10. It really doesn't matter to me. I ignore it. It doesn't matter. But there's also a step 0, actually, right? The step 0 is to find the powers of 10. Because sometimes they're hidden away into 2s and 5s. So you want to really pull out all the 2s and 5s first before you start this approach, right? Let me give you some questions. Right, let's look at this. 12 times 2 to the power of 2 times 5 to the power of 2 actually has 2 zeros, right? Because you can just combine the 2 and the 5 and make it a 10. But what about this, right? 1 times 2 times 3 times 4 times 25. How does it have no zeros, right? Because after all, we can't pull out a 2. We can pull out 1, 2, but we can't pull out 5. Right? It seems here there's no 5 here. So what do we do? Actually, we have to notice that 4 and 25 can be written as 2 to the power of 2 and 5 to the power of 2, right? And once you do that, we notice, oh, there's a 5, oh, there's a 2, right? Let's combine the 2s together first, right? If that wasn't clear, let's go back. 2 times 2 times power of 2. I'll combine them together. And now, I'll be able to say that there are 2 zeros. Because there's an extra 2. It really doesn't matter. We can't use it, you can't combine it with another 5 anymore. So, whatever there's extra, we don't count, right? We count the number of 5s, the number of 2s, we pick a smaller one. So back to this question, right? How many zeros are there at the end of this entire expression? We're going to count the number of factors of 5 first. We count 5s, and then we count 25, and then we count 125 and 625. Again, the reason why is because back here, 25 doesn't seem to have a 5, but it has 2 powers of 5. So be very, very careful of that. Alright? So if you want to count all these factors of 5, there will be 10, 25, 40, 55, all the way up to 700. Right? The reason why is because each distance is a distance of 3. So to move from one factor of 5 to the next one, we can just do a very quick listing and we realize it's 10, 25, 40, 55. Okay? We're going to notice that, oh wow, there will therefore be 60 factors of 5. And clearly, we know that from here to there, right, from the start of 1 to 700, there will be at least 60 even numbers. So, again, we pick the smaller number, right? There are smaller numbers of powers of 5, so we know that there are 60 zeros at the end of the product. That's the question in a nutshell. Okay? So let's extend this question. How many zeros are there at the end of 25 factorial? Okay? And we're going to further extend it. How many zeros are there at the end of 20 choose 4? Right? And if any of you have forgotten the choose operation, it's right there. It's m factorial divided by n factorial divided by m minus n factorial. Okay, so try this question, really think about it, and we'll go through that in the next lesson.